All right, that's weird. My Oh my goodness, I just realized why this is not dinging for me. Let me see here. Let me unmute this site. There we go. All right, welcome guys. If you're watching on the recording, we're working on this warm-up today, and I'm giving everybody a couple minutes to try this out. See if they can answer it out for me. Given this table, right? From the interval from -3 to 10, they have some specific values for the function, specific values for the derivatives at those points, and the second derivative values at those points as well. They tell us that the first derivative only has 2 zeros on that interval, and the second derivative has only 2 zeros on that interval as well. Okay, so there's no other zeros, only those two that are shown on the table. Right? And yeah, from there, we need to figure out if we can find out where f has a relative minimum, where f has a relative maximum, and where f has a point of inflection. All right, give me those three things right there. And then after that, this is a review question right here, which is, what is the equation of the tangent to the curve y is equal to f of x at x equals to 5? At x equals to 5. Okay. So that's what we're doing right now. I'm giving everybody a couple minutes to try this out. Once you've tried it out, we're going to go over it and see what you guys got. See what you guys got. Yep. There we go. Okay, that should be better now. Oop. Let's see here. How many answers we got here? Good. A good 18 of you have clicked in, but only a couple of you have tried writing out something. You could also just type it, right? You could also just type it for this one. You can draw it out if you want. You can draw it out if you want. I see we have a couple of questions, a couple of worries, a couple of concerns. So this is a little bit different, right? We've done a lot of these problems before, where they asked us to find where it's increasing, where it's decreasing, where is the critical point, right? And if you guys remember, we did it when they were just giving us the actual function, right? And we kind of worked through that process a lot. We know that if you take the derivative, right, the first derivative, when you solve for it when it equals to 0, that tells you that you have critical points that you then go and test around those critical points to see if that is a max or min. And it all depends on whether or not the derivative is positive or negative to tell you if the original function is increasing or decreasing. We did a lot of those problems, right? We did quite a few of them actually, but now is when we actually try to see if we actually understand what it is we were finding, right? And that's the whole point of this warm-up right here. I shouldn't have scrolled away because I realized some of you guys are still answering these questions. But that's what we're going to do today. We're going to try to make those connections to see if we are getting it, we are understanding what it is we're finding. And if you're struggling right now to answer this warm-up, don't worry about it. It's the first time you're seeing it, so it's a little bit different. It's a little bit different. Okay. It's a little bit different. So let's see here. I want to reward those people who are trying their best at this or are trying to answer it. Don't leave it blank, guys. Just try to get an idea of what does it mean when it's asking you for relative minimum, right? And if you need a hint right now, right, relative minimum, remember, happens at a critical point, meaning the first derivative, that's this guy right here, right? This right here is the first derivative, right? And this is the second derivative down here. Remember, critical points occur when the first derivative is equal to 0. So you just look at the table and see if you can find where is the first derivative equal to 0? Where is it at? Right? And where is this part up here, where x is, right? If x is equal to, let's say, 10, then these are the values for where x is equal to 10. Okay? And that's all that is. Right? That's all that is. So it's going from -3 to 10, and you have some specific values there. Okay? And where let's see if we could find out where our relative minimums occur and where our relative maximums occur. Okay? All right. That's that idea there. So hopefully you can give it a try, give it a shot, and see if you can list at least where the critical points are. And then after that, then you can try to figure out if you have a max or you have a min, right? If you have a max or if you have a min. While you guys are doing that, I'm going to open up, let me see here. I'm going to open up the Cardinal Points app so I can give you guys your points for that. I'll wait for this computer to boot up. Right now, I have about 16 of you guys who have attempted something, right? Who've made a mark, who've made a drawing. I'm going to give you guys those points. Give me a second there. Let's open you up. So at least write out A and see if you can try to figure out what it is. For those of you guys who keep drawing those markings who don't do anything on here, you should be able to do D. You should be able to do D. That's not something from this chapter. This is something from the first time we started learning about derivatives and calculating equation of lines based off of that. You guys should at least be able to get that. Don't just leave all of it blank. All right, that is not the strategy you want to take when we're getting closer and closer to this AP exam. When you guys take the AP exam in May, you should never leave any of them blank. You never lose points for writing down stuff. You miss out on points if you don't attempt anything, right? So you should write down something. You should try something, even if it's something you're not sure of. You try to piece it together. That's what I'm telling you right now. You should try to take that strategy when you do these problems. If you can get 1 point out of 9 on a free response question, that's already a good start. Okay? Never be happy with just a 0 in there. Don't just leave it blank. Write down something. Get into the habit of that. All right, let me see here. You guys are my period 3. Here are the names that I've seen answered already. Let's see here. We got Ava. We got Jocelyn E. I see you in there. Monica M. I got you. Where are you, Monica? There you are. David. I got you. Let's see here. Are you set up? No, you're not for that one. What you? There we go. All right. So we got David. We got Kaylee. Got you. Alvin. Got you. Julia. Got you. Brandon N. Wait, no. Brian N. There's no Brandon N. Brian N. Juliet V. Got you. Gracie F. Got you. Emily C. Got you. Brian B. Got you. Jeffrey. Got you. Fatima S. Got you. Max. Got you. Leslie. Leslie R. There you are. There you are. Aurelie M. I got you. Thank you for clicking on there. Aurelie. Angela, got you. I see you typing out something there. Angela. Boom. Joe. Where are you, Joe? Joe. Come on. There you are. Sam, got you. And Diana, got you. There's a couple people still haven't clicked in it or haven't written anything yet, but hopefully you will. And you can join and earn these points. Earn these points, right? Yeah. All right. Let's give you 3 points for your commitment here. Boom. Easiest points you'll ever earn. All right. All right. Let's see here. So that was that. What else are we going to talk about? Okay. So I'm trying to tell you guys right now. So this, like, I have to make this conversation every year for some reason. I don't know why, but a lot of my students, when they come into AP Calc, oh, don't worry about Brandon. You're here now. That's what's important. You're here now. All right. So a lot of the things that, not a lot of things. One of the main things I always seen that my students struggle with when they come to AP Calc is that they feel like they need to know how to do the problem 100%. And if they don't know how to do a problem 100%, they don't bother with the problem. And that's not the best way you should be attacking math problems, right? What makes math problems fun is actually working it through each of the steps along the way. And I know that sounds ridiculous, but because a lot of the times you guys are like, oh, that's an easy thing. You just do this and you go from A to B and you're done. What you don't realize, though, a lot of these more difficult problems are going to take a couple more steps. And I think it's a little bit more fun figuring out the steps along the way, if you can get yourself to believe that, right? Like for this problem, for example, we have learned how to find a relative minimum, right? And I'll tell you this right now. You have heard me say this before. You know that a relative minimum occurs around a critical point, right? Around a critical point. First thing first, right? When you're asked to find a relative minimum or relative maximum or extrema or whatever you want to call it, right? We always have to find these critical points, which means we're supposed to take the derivative of the function, right? And a lot of students will forget that because they'll look at this right here and they'll say, okay, critical point, relative minimum, critical point, I need to find the derivative. And they'll look at this table and shut down because there's no function there for me to take a derivative, no power rule needed, no chain rule needed, right? And they'll just say, that's different, and they won't do the problem. And this is where it's frustrating to me because they give you all the values for the first derivative, and it's all right here. It's all right here. You see that? They give you those values. You don't have to do any work to find the derivatives. They give you those values. And to find the critical points, right, you just care about where does it equal to 0 and where is it undefined. So here are 3 critical points right there without having to take the derivative and without having to solve it algebraically, right? And where are they occurring? They're occurring at x equals to 1, I'm sorry, x equals to -1, x equals to 3, and at x equals to 7. Now that doesn't mean they're all relative minimums, right? That doesn't mean they're all relative minimums. The next thing you have to do after you find your critical points is to test points around them, right? We remember that? We drew these little lines here at these critical points, and then we would test values between them. So we would test a value that's like less than -1, right? We test a value that's between -1 and 3. We test a value between 3 and 7, and we test a value from 7 and on, right? If you look closely, they do that for you. You see that? -1, number that's less than that, -3. From -1 to 3, they test a value between that for you. From 3 to 7, they test a value between that for you. And then everything above 7, they test that for you as well. So they already test them, and they tell you right here that this is a positive number right here. This is a negative number. This is a positive number, and this is a positive number. So they already do the signs for you. They already have that tested. This is a positive, this is a negative, this is a positive, and this is a positive. They already do that for you, right? And if I'm looking for something that is a relative minimum, I'm looking for something that has a decreasing value, where the function is decreasing and then changes to increasing, which means the first derivative should have a negative sign and then changes to a positive sign, right? So where does it change from a negative sign to a positive sign? And that's right here. See that? That's right there. And that's all the first derivative test is telling you, right? That's all the first derivative test is telling you. So where do I have a relative minimum? I have a relative minimum at x equals to 3, right? Because the derivative, right? The derivative changes from negative to positive at x equals to 3. And that's it. And on the AP exam, you don't even need to, on the AP exam, they will give you a problem like this, and you have to be able to read these charts, right? We've done it analytically. We've done it algebraically, right? But now we're doing it just by looking at numbers on a table, and we got to be able to see if we can find that right there. All right, hold on a second. Yeah, just had to fix something under the table real quick. All right, there we go. Okay, so I'm gonna pause there for a second. Are there any questions for part A right there? All right, any questions about that? Any concerns? Does it make a little bit more sense? All right. this is where you got to let me know, guys, because I don't know if you're okay or not, unless you say so. And if you don't say anything, I kind of just assume that you all get it. What do you guys think? You good? You're not good? You're terrible? Well, I guess hold off on that for now, and then I'll put up a quick check with you afterwards. Okay. Now here's my issue with this method, though. So this is a standard method that people do. They'll give you a table, right? And it's very similar to this right here. Now, this is the important part, though, right? They tell us that the first derivative only has 2 zeros. That's actually very important. That's actually very important. And they actually show you the 2 zeros right there. If this statement was not made, right, I cannot guarantee that this right here is the only relative minimum, or if it actually is a relative minimum. Because here's the thing, right? They picked random numbers, right, from -1 to 3 for you. They picked 1 for us. What if someone else, you know, what's going on at x equals to 2? They don't tell us that, right? So for all I know, at x equals to 2, the derivative, right, could have been some other value right here. Now here's the thing, though. Since they made this statement right here, that it's guaranteed that there's only 2 zeros, at x equals 2, I can't have a positive value there. Can anybody tell me why? Why at x equals to 2, why can't the derivative be a positive value if they're telling us that at x equals 1, I have a negative value? What's something that's preventing me from saying, hey, at x equals 2, what's preventing me from saying that there's a positive value there? And if that were the case, by the way, if at x equals to if x equals 2, we have a positive value, and then x equals 5, we have a positive value, that's no longer a minimum, right? And Monica is saying it right there in the chat, and Brian as well, right? There would have to be a 0 in between them, and that means it would cross the x-axis, making another 0. So that's the key thing right there. Good job for both of you guys. Thank you, Monica. Thank you, Brian. You know what? I'm gonna start giving out more points for that. Let's go here, Monica and Brian V. Thank you for your ownership. We'll go with that. And yeah, that is correct. If they don't make this statement, then that is a total possibility that x equals 2 could have a positive value there, which stops you from saying that this right here is a relative minimum, right? But thank goodness they say that right there. Therefore, there's no other values that will make it cross the x-axis, right? It won't go from negative to positive there, okay, for that derivative. So what if they didn't make this statement right here? What if this was not actually said, right? Is there a way for you to still see that you have a relative minimum or a relative maximum just by looking at the table? And I'm going to let you guys know right now that there is, right? So aside from us learning about the first derivative tests, right, telling us when is a function decreasing or when is a function increasing to tell us a minimum, or increasing to decreasing to tell us if it's a maximum, right? What if we only had the point? What if we only had the point and we don't have the increasing or decreasing around it? We can still figure out if something is a minimum or a maximum or not based off of its concavity. Based off of its concavity. So if I know that a function is decreasing and then increasing, and I have a relative minimum there, that means the second derivative should be positive because it has a concave up shape. If you have something that's concave up with a critical point, that means that you have something that you're dealing with as a minimum at that point, right? Secondly, if you have something that's increasing to a decreasing, right, but you don't know that, you only know that it's like this, and it's something that's concave down, meaning the second derivative is negative, then hopefully you guys can see that you're dealing with a maximum. So if they don't tell you this part right here, that you only have 2 zeros, or you're dealing with issues where you don't know if the thing changes sign closer to that, then another thing you could do is look at the second derivative, right? Look at the second derivative. So right now we're going to deal with looking for the relative maximum, right? Relative maximum. So when you're looking for the relative maximum, again, you're looking at these critical points, but instead of seeing the sign change, right? Because let's say, just pretend right now we don't know if there's a 0 or not, but we do because they tell us that right here. We can just use the second derivative to help us out. The second derivative being, if it's concave up or if it's concave down, right? Remember, if it's concave down, we have a maximum. If it's concave up, we have a minimum, right? That's what this looks like. So now we're combining things together, looking at the first derivative, critical points, and looking at the second derivative, if it's a max or a min, by seeing if it's concave up or concave down. Okay, so check this out. So we have our critical points still, here, here, and here. But now I'm also going to look at the second derivative at that specific point, right? I'm also going to look at it here, here, and here. Now, I'm looking for a max, which means that it needs to look something like this, which means that it should be concave up, right? Which means that the second derivative should be, wait, I did not mean to say up, concave down, not me concave down, right? Which means the second derivative should be a negative value, right? The second derivative should be a negative value. So right here at x equals 7, I have a critical point, but my second derivative is 0, which means I have a point of inflection there, which means that this is neither a max nor a min. It's neither a max nor a min, okay? Over here at x equals to 3, we already said it was a relative minimum, but we can double check it by seeing this right here. This is a positive second derivative, right? Which means that this is a concave up problem, which means that this critical point is actually a minimum. It's actually a minimum. And then over here, we have a negative value right there at this critical point. So right here, we have something that's concave down, and I have a critical point that's there that's telling me that this has to be a relative maximum. That's why for part B right here, I have a relative max at x equals to -1. And all I would state is that the first derivative is equal to 0, and the second derivative, right, is less than 0, meaning it's negative, meaning it's concave down, making a maximum hump, right? A little hump, a little top shape there. So, right, f prime of x is equal to 0, and I'm sorry, f prime of -1, right, is equal to 0, and f double prime of -1 is less than 0, and that's all you really need. If you have it equal to 0 and the second derivative is greater than 0, then you have a minimum, okay? And that's it. That's it, guys, for part B. So x equals to 3 is my relative minimum. X equals to -1 is my relative maximum, okay? And let's go ahead and go down to here for part C. Identify all x values where f of x has a point of inflection. Point of inflection is where you only look at the second derivative changing signs, right? Changing signs. And again, I can't stress this enough. You can only do that for this problem because they state that the second derivative only has 2 zeros. There's no other zeros than the zeros that they have listed there, which is here and here. And all you're looking for is where does it change sign? So you notice for the second derivative here, you have it going positive to positive. So this right here is not a point of inflection, right? Whereas this one is going from negative to positive, this one is a point of inflection because we actually have the sign change from here to here. So for part C right here, we have a point of inflection at x equals to 1. By the way, I'm hoping you guys are starting to see the where, right? These are my x values at the top of this chart. So you guys got to get used to reading these tables, okay? So that's where it's occurring. Everything below it is what the values are for the function, the first derivative, and the second derivative, okay? All right. That's that one right there. Before I move on, I'm going to go ahead and just ask you guys right now, how are you guys feeling about this? Let me see here. I can bring this up right here. I want to go ahead and ask you guys, how are you feeling about this? Give me 1 second. Just let me know real quick. How are you guys feeling? Thumbs up, thumbs down, somewhere in the middle. Just for these first three. Don't even worry about the equation of the tangent. Like I said, that's an older topic. But for right now, how do you feel about figuring out if you know where something is a relative maximum or where something is a relative minimum based off of that information that is given there? You guys let me know. Let me see. How are you guys feeling about it? You're spread evenly. Some of you guys dead center. Okay, so with the table, it's kind of fair because this is me the first time you're seeing it with the table. So kind of spread evenly along, so that's fair. That's fair. What if, and now hold on to those thumbs real quick. what if I didn't have it as a table, but I gave you a problem like this? You guys, real quick, don't actually solve this problem. Just give me a thumbs up, thumbs down. If I gave you a problem where I gave you a function f of x was equal to, let's say, the square root of x cubed plus 1, right? And I asked you to find the max, the min, the relative max and minimum for this problem. Can you guys move your thumbs up, thumbs down for a problem like this? What if I gave you a problem like this? Would you guys be okay with it? Are you less okay with it? Are you more okay with it? Or are you still the same spot? What if I gave you this problem? How would you feel about that? If I asked you to find when does the first derivative equal to 0? When does the second derivative equal to 0? And then making the sign chart for this one. How do you feel about that? Okay. So you guys are a little bit more comfortable with this one because you've been practicing more with this one. That's perfectly fair. So that's good. That's a good sign. So that shows me that you still remember how to find your max and your mins, right? So all I'm trying to say for today's part, for this warm up right here, is it's the same. It's just, sorry, my dog just whimpered. It's the same thing. It's just in table form, right? They do most of the heavy work for you. That's the part that you guys got to get used to, I guess. So there is a homework problem that has a table, so maybe you guys want to take a look at that and see what it is. And if you're still struggling with it, please stop by during office hours and we can go over that problem. Okay, so we can talk about that. Oh yeah, that's good. That's good. Oh, it's good to know. Good to see where you guys are at. All right. Sorry, I'm getting distracted by my dog. Okay, last problem right here. Let's finish this up. Let's finish this up right here. Last one is asking for us to write an equation of a tangent to the curve y is equal to f of x at x equals to 5. So these are the things we're going to be focused on right here, right? I need to write an equation of a line that's tangent there, which means that I'm looking to find what, remember the equation is y minus y1 is equal to m times x minus x1. Give me 1 second. My dog wants to go outside. All right. Yeah, go ahead. Wait, do you want to go like outside? Here you go. Can I go outside? All right. Sorry about that. So remember, this is an equation of a line that we're going to be using, right? Now they're telling us that it's tangent, which means we need to find the slope of the tangent line, which is equal to the first derivative at the point that we care about, right? And the point that we care about is at 5. So the slope of the tangent line is going to be the derivative value at 5, at x equals to 5, right? So what's the derivative value at x equals to 5? They tell us right there, it's equal to 2. So I know what that is going to be. That's going to be a 2. The other thing we need to find then is the y1 and the x1. Well, x1's already told to us, right? x1, they're telling us that it's going to be at x equals to 5. So that's going to go right there, right? And I just need to find out what y1 is, but y1 is just going to be equal to what the function value is at x equals to 5. And that's going to be equal to this guy right here, that 3 right up there. So I'm looking at everything when x equals to 5. And that means the y value, or the output value, is going to be 3. And that's going to go right there. So what's my equation of a tangent? Y is just going to be y minus 3, right? It's equal to 2 times x minus 5. And that's it for that one. Don't forget this, guys. You guys are going to have to write equation of tangent lines. It's one of the main things of calculus, right? Because when you're finding a derivative, all you're doing is finding the slope of that tangent line. And if you want to find the equation of that said tangent line, you got to know how to write an equation of a line. All right? So that's that one right there. All right. How you guys doing? You guys all right? Hopefully you guys are. Feeling a little bit more confident with like these derivatives and whatnot. Oh, also, thank you guys for last week for actually doing the Delta Math work. I put it in as a extra, shoot, I need to go fix that. It's supposed to be an extra credit quiz grade. So congrats to those who actually attempted it. Even if you didn't get 100%, it's going to go in as extra credit towards your quiz grade. And if you didn't do it, then it just doesn't count towards anything. And no, you can't make it up because it was one of those things that was just for those, if you were there, I couldn't make it to class there that day because of my own family issues. But if you were able to attempt it, right, if you did 100% of it, then you get basically a full-on extra credit A grade towards the quiz and any future quizzes. And if you got like, any percentage of it, it still gave you that as extra credit. I just need to go adjust that on PowerSchool, because right now I think on PowerSchool it's saying that it's a regular quiz grade. I need to put it in that it is not a regular quiz grade, it is a extra credit quiz grade. So thank you for those of you guys who were kind enough to work on that during my class last week when I couldn't be here. Okay, so go ahead and take that into account. Someone let me know though if the changes doesn't get made before your progress reports. I think your progress reports are coming up soon. I think. Let me double check. When are your progress reports due? Progress report is due next week on the 18th. So I should hopefully have that fixed and updated by then for you guys. Okay. All right. Let's go for today's lesson, right? Today's lesson here. All right. Let's take a look here. We are going to be, today, we're going to be sketching. Why am I going to write this out? Let's type this out. No, let's type this out. We're going to type this out. We're going to be going ahead, and today's lesson is going to be sketching graphs of functions and their derivatives. Boom. Let's make that a little bit bigger so we can all see. Boop, boop. And what size are you? 11. Let's go with 28. Bam. There we go. For today's lesson, all right, we're going to go ahead and see if we can sketch the graph of the function given their derivative. All right, we're going to start off with that today. Okay. All right, let's see here. So again, it's more of we did this on Desmos last week, right? We were trying to figure out if we could figure out which one is the original graph, which one's the derivative, and which one is the second derivative. Now we're just going to go ahead and do this freehand, and we're going to go a little bit backwards. We're going to be given the derivative and try to see if we can sketch what the original graph is going to look like, right? So let's go ahead and take a look at one of these example problems right here. So I'm going to go ahead and get this right here real quick. Give me 1 second. And then we're going to see if we can go ahead and sketch the graph based off of that. Boom. All right, there we go. Can you guys see that? Of course not, it's tiny. Let's go and make that a little bit bigger. All right, there we go. So on the left there, we have a graph of a derivative. Is it like some of the problems we had on homework on 4.3 assignments? It's possible. Wait, yes, there was a couple of them where you were given a derivative and they're asking you to sketch a possible graph of the original function. So yes, that is yeah, well, a couple. I think it was like maybe 1 or 2 problems that had that on there. So we're going to go over this right now. Hopefully that answers your question. Hopefully. All right, check this out, guys. Check this out. The derivative is telling me that the slope of each of the tangent lines in the original graph is always going to be equal to 2, right? Which means the function that we were originally dealing with is always going to have something that has a slope that's going up 2 over 1, and it never changes, right? So what would that look like? Well, that would look like something like this, right? If I was drawing this out, it's supposed to go up 2 and over 1, up 2 and over 1, right? So, and that thing is going to stay constant all the way through. It's going to stay at a positive 2 the whole time. So my function is always going to be going up, right? It's going to look something like this. And that's it. There is a possible function that has a derivative of 2, right? And that kind of makes sense, doesn't it? Because if I'm looking at it, you know what this function actually looks like to me? This function is actually 2x, right? This function is actually 2x. If you were to graph 2x, right, it's just a line that's going like this, right? And if you take the derivative of that, the derivative of 2x, y using the constant rule and the power rule, y the derivative of that is just equal to 2, which is exactly what we have graphed here. You guys see that? Can somebody give me a graph that would also satisfy this, but looks a little bit different from mine. I'm opening up Pear Deck for you right now. Can somebody sketch a graph that would have this same slope, but would look different from mine? Right? Can you guys go ahead and try that real quick on Pear Deck? Which one? Which you want to go inside or outside, dog? Make up your mind. You want to go outside? She doesn't like closed doors. All right, go ahead right now, guys. Try it out. Can you draw? What do you think a function should be that would have the slope of a tangent line of equaling to 2, but it's going to be different from my line? It's going to be different from my line. What do you guys think? Give it a try. She knows that she could push it open. I close it like, no. Close it like right here. See? She can push it open if she wants to come back in. All right. Here we go. You ready for this? You ready? Check this out. Whoever drew this dot has the right idea. Oh, there it is. There you go. It's the same line except shifted up, right? That's perfect. Whoever drew that right when I moved this onto the screen. Good timing, whoever that is. Let me check who that is. Good job. Is that Brian? I'm thinking it's Brian, but good job. Good job. And then second person right here, same idea, except it's moved down, right? It's a possible function. It's not guaranteed. We don't know which one's the correct one, but we know it's a possible one, right? We know it's a possible one. This person's moving ahead of me right here. So be careful with this, right? X squared is an interesting function that we should be looking at, but you're giving me the one before 2x. Does that make sense? Because the derivative of x squared would give you 2x. So what this sketch is right here, this is technically the derivative of what you just drew. Oh no, don't erase it. Don't erase it. It's wrong, but it's a good wrong. It's one that we can learn from. Okay, so what you've drawn is actually just getting ahead of me. That's all. If this was the derivative, right, being negative here and then positive up there, you see here it's okay. You can see that you have a slope that's going down, right, which means that it has a negative slope, and then the function's increasing over here, which means you have a positive slope, which is what happens when you have it shifted like that, right? But yeah, not bad, and very good up here. This is beautifully drawn right here. Good job. Yeah, same thing. As long as your line has a slope of 2, right? As long as your line has a slope of 2, then it's following, right? That first one right there. It's following this derivative, right, of having a slope of 2 for all the values. Okay. Now, whoever was doing that earlier kind of beat me to the next punchline right here, which is part B. Part B right here. Let's go ahead here and let's take a look at this one and see if you guys can try this out. Can you guys sketch a graph? I mean, I already gave this away, but I still want you guys to try it. Can you guys sketch a graph where the derivative looks like this, where the derivative is this line right here, has a slope of 1, has a slope of 2 here, it has a slope of 3 there, it has a slope of 4 here, it has a slope of 0 here, has a, I'm saying the tangent line. So I'm going to go ahead and clear out your screens. I'm going to ask you guys to do this again. So let me go ahead and new prompt that and make that drawable. So can you guys go ahead and try it for this one right here? What do you think that is going to look like? What do you think that function will look like if the derivative is graphed like this? So remember, right, at this point right here at x equals to 0, right, I have a tangent line that's horizontal. I have a horizontal tangent line at x equals to 0 because that's what's happening right here. And then at x equals to 1, I have a positive tangent line, meaning the function should be increasing. So it should be going up, right? So what do you guys think? What's the possible function for this one right here? Calvin, ironically, if you take those dots out, you're very close to what the function should look like. Just draw it as a smiley face and take out the eyes. Wait, that gives away for everybody else, doesn't it? Almost everybody else. All right, so what does this graph look like? I see a lot of you guys sketching your graphs on there. There's pretty good ideas there, right? Pretty good ideas there. But now here's the thing: where it's going to be is something we don't really know, right? And we got to be okay with that, right? But check this out. Check this out. You ready to check this out? You just kind of pick a point, and for now, we just pick a point and let it exist there. So, for example, I'm going to just go ahead and go to 0 right here, and I'm going to pick a point right there, right? Now, what I know is happening is everything that's to the right of 0 is increasing faster and faster. It's going to have a slope of 1 right here, and then at 2, it's going to have a slope of 2, so it's going to be a little bit steeper. And then at 3, it's going to have a slope of 3, so it's getting steeper and steeper as I go more and more towards the right. See that? It's steeper in the positive sense because this value keeps increasing, right? So this is telling me that at this point, my slope is equal to 1, then my slope is equal to 2, then my slope is equal to 3. And if you can imagine that, right, the tangent line of 1 would be something like that, right? And then the tangent line of 2 would be a little bit steeper. And then the tangent line of 3 is even steeper, right? So that's what's occurring right there if I'm taking that into account. I'm looking at the slope of 1, 2, and 3. Slope of 1, slope of 2, slope of 3. See that? And that's how we're reading this here. This graph of this line is just telling us that the slope at these particular values is getting bigger and bigger, which means that it's still positive, it's still increasing, but it's increasing faster. So it makes this line kind of curve upwards. See that? Kind of curves upwards. Okay? And then if you look over here, right, you have a slope that is -1, a slope that is -2, and a slope that's -3. Same thing. As I go this way, it's getting steeper and steeper, but it's getting steeper and steeper in the negative sense. It's coming down like this until it reaches 0. And when it reaches 0, my tangent line flattens out right there. So it's very steep negative, a little less steep, and then flattens down right there. And that's what my function would look like. My function looks like a parabola, right? And I'm hoping that makes sense because we have very negative slopes, we have very positive slopes, and then we have 0 in between. So it kind of like goes down and then flattens out and then goes back up. So the function is decreasing slowly. It's like decreasing a lot, decreasing a little bit less, decreasing a little bit less, decreasing a little bit less right there, all the way down to not decreasing at all because you have it equal to 0. And then it starts to increase. So the derivative is now positive, right? And it's increasing more and increasing more. And it just keeps following that suit. Yes, Calvin, anything is possible. Now, here's the thing. The part that I'm trying to make sure you understand is we don't know if it actually looks, or if it actually goes at that specific spot, right? The tricky part about this is this could be anywhere. It could be down here and still have that same derivative. It could be up here and still have that same derivative. Where is it supposed to be? And that's one of the things. We don't know. It has infinitely many possibilities. And we're going to talk about that in the future. But for right now, I just want you to draw one possible one. And you can make it high, you can make it low. As long as it follows this right here, then that's pretty much good to go. Right? It looks like everybody drew it around the origin. So, great minds think alike. They like to think about it around the origin. Oh, no. There's one person who thought outside the box and put it down at -3. Good job making it look a little bit different. Good job there. Leslie, good job making it a little bit higher. I don't know if you did that on purpose, but it's still correct, right? It's still following the answer that we have there. Okay? Still following the answer that we have there. All right, let's keep going. I know some of you guys are like getting it already and some of you guys are not, so don't worry if you don't get it yet. This for sure is, it takes some time. This for sure takes some time to grasp fully. So let's do another one. Let's go. Boom. Let's take a look at this one right here. What is happening for this derivative right here? And what do you think the function should look like? What do you think the function should look like for this one? This one is an interesting one. What do you guys think? I'm going to go ahead and give you another blank slate. Oh, I'm sorry if you already started drawing. Don't hold on a second. Don't draw just yet. I need to give you guys a blank slate for those of you who had drawing, so I'm going to clear this out for you. Boom. There you go. That way you can sketch on a newly fresh one right there. Oh, yeah. Oh, some of you guys already caught on to this one. Ooh, who did that one so quick? Good job. Some of you guys got that already. Now, that's not bad either. You got the right idea for seeing that it's all negative values. So this thing should be decreasing for the whole interval, right? From -5 to +5, this thing should be decreasing, going down. But the thing is, it's decreasing differently each time. David, what are you drawing? I just looked over and like, what? But yeah, it should be decreasing for the whole interval. But here's the thing though, it's not just decreasing at a steady rate, right? It's not just decreasing straight down like this, right? Because at this point right here, I don't know if you guys see this or not, the derivative at this point right here is 0, which means that at 0, my line should be kind of flat. My line should be kind of flat. So if I just draw a negative slope all the way through like this, you see how right here at this point right here, that has a tangent line that's negative, which counters this part right here, which tells me that the tangent line should be 0, right? The slope of that tangent line should be 0. So as well as that drawing is very nice, David, you still got to have something that flattens out at x equals to 0, right? I can't just have it go straight down like this because that's skipping over the fact that the tangent line should be horizontal there. So how do I fix that? How do I fix that? Well, here's the thing. What that looks like, if for it to decrease and then flatten out, it looks something like that. You see that? It's going down, it flattens out, and then it still goes down. So here's a function that's decreasing, right? You see it decreasing, and then flattens out right there, and then goes back to decreasing. See that? So it's decreasing, 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 flattens out, and then continues to decrease. Wow, David, that's actually not a bad edit. But can you... that middle part, though, still needs to flatten out a little bit more. But other than that, though, that looks pretty... All right, I'm sharing that with you guys here. Putting them... wait a second. Why are you not... Oh, show responses. I know how to use technology. So he's got the right idea. It's decreasing, 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 decreasing. But right here, it needs to flatten out right there. It needs to flatten out. That's all it is. Now, what else we got? Anyone else? We got some good ones here. Anyone likes to draw it around the same spot? That's not bad. That's beautiful, actually. Nice flatten out right there at 0, right? We got something increasing here, and we got something decreasing. I'm sorry, decreasing here and decreasing there, which follows along with those right there. So this one right here is the common mistake for this problem. I'm just letting you know right now, because everyone sees that it's decreasing because the derivative that they have shown here is all negative. You're not wrong. It's all negative, meaning that it should all be decreasing, but they're decreasing at different rates. And you also have a critical point here. Okay, that critical point is telling us that we need to have a horizontal tangent line at 0. Right there, we need to have that horizontal tangent line, right? That point right there. That is a very important point. That's telling us that we have that horizontal tangent line. So please make sure you take that into account. Also, understand that these are more negative than the further away they are from that origin. So right here we have a slope that's -3. Over here we have a slope that's -1, right? So I'm hoping you guys can see the picture here, right? At x equals to 4, you have something that has a tangent line that has like a slope of -4. And then as I get closer to it, right here at 2, I have a tangent line that's a slope of just -1, right? That slope right there is just -1. That slope up there is -4. So you see the slope of that, the curve there should be changing because the tangent line is changing along the way. It's not just going to stay at -4 all the time. It's not going to stay at -2 all the time. It's not going to stay at -1 all the time. It's changing ever so slightly as I move along, which means the function is curving so that it approaches this little flatten out area right here, where right here the slope is equal to 0, right? The slope of the tangent line is equal to 0 there. So hopefully you guys can make that and spot that difference there. So that's why this function is looking something apply for that. Does that hopefully make a little bit more sense? Right. And again, if you want a variation of this, right, you can also just draw it like here. That's one possibility. That's another possibility. As long as it flattens out and it's decreasing more and more as it goes down. Okay. So that's that one right there. All right, guys. Hopefully that makes a little bit more sense. Wait, did someone raise a hand or did someone just join? Or someone leave? Oh, well, we'll figure it out.
I joined. Sorry, Mr.
Oh, no worries. No worries. No worries. Okay, so let's see here. Let's try another one, guys. This one, I want you to try this one on your own. Let me see what drawings you guys get for this one. Okay, so let me go ahead and take a screenshot here. Like so. And let's see you guys try this one out. Try this one right here. This one is a little bit different because, oh God, hold on. This one is a little bit different because they tell us where one of the points passes through. Where one of the points passes through. So now we don't have infinitely many options. We have one particular option. And this one is a doozy of a curve. That's right. I said doozy. See if you could try to figure this one out. I'll give you guys a minute for this one. This one's going to be a little bit more complicated, right? So keep in mind when you're drawing this sketch out, the original function is going to be increasing from here to here and from here to here. So it should be going upwards on those intervals from -4 to 2. And then it's going to be decreasing from here to here and from here to here because they're negative derivative values there, right? So sketch your graph out accordingly. Sketch your graph out accordingly. Like that. Go ahead and take a look at that. Oh, I can't close the door. Dog has her paw right there. Okay. All right. So try it out, guys. Try it out. What do you guys think? Yeah. Let's see, where are you guys at? How's your wait? Did I clear out the graph for you? I did not clear out the graph for you guys, did I? Oh, that's okay. Some of you guys just deleted it and redrew it. So yeah, you guys are. I'll just leave it for there for those of you who are working on it right now. Just sketch this graph. Oh, shoot. Let's put that back up there. So delete the graph that you have right now and try it right now. See if you can try to see what this graph should look like. And I try to give you some hints, right? The blue lines is where it should be increasing at. The red lines right there should be where it's decreasing at. You also have critical points, right? At x equals to 4, x equals to -2, and x equals to -4, because that graph tells you where, right, the first derivative is equal to 0. Oh, that's a key one right there. They tell you that it's passing through the point 4, 2. So that is a key point right there. That is a key point right there, which happens to be a critical point. Now, is that a relative max or relative minimum? Do we know? Wait, did I draw that wrong? -4, 2. No, that's right. -4, 2. That's the point right there. That's good. There you go. Oh, excuse me. It's so yawny today. Don't worry about it being perfect, by the way, guys. Don't worry about it being perfect. Just try your best on there. Okay. All right. I want to take a look at what you guys have attempted. Okay. I want to take a look at what you guys have attempted. So let's see here. So if you guys could check this out real quick. I want to share these examples right here. These are really, really well done. So here's one. Good job, right? Showing it is decreasing until -4, and then it's increasing until -2, and it goes back to decreasing, and it decreases for a while. It decreases for a while until you get to 4, and then it goes back to increasing, right? And if you follow along with that, that's right here. See that? I have negative derivative values here, which means that the original function should be decreasing. Now, is it decreasing here? Is it decreasing here? Is it decreasing here? All that matters is that it decreases and it hits this point right there. So it's decreasing. I don't care like if you draw it with a curve, right? I don't care if you draw it as a straight line, right? But technically it's going to be with a curve because it approaches the slope of 0 right there. So it needs to kind of curve into it like that right there, which is what we have drawn on our examples right here. So very beautifully done. Oh, yours is a little bit lower, but that's okay. Your derivative is still correct. You're just missing out on the information they give us later on, which is it actually needs to pass through the point -4 and 2. So it needs to be decreasing and hits this point at -4, 2, right? That's the key thing right there. So let's take a look at the next part of it. Everybody's got the right idea here. The next part from -4 to -2, the function needs to be increasing. It needs to go up, right? It needs to increase until -2. All right, so let's go ahead and take a look at that right there. You can see it, right? This blue line shows me that my function should be going up all the way until 2. All the way until 2. So it should be going something like this. Now, how high up does it go? I don't know. Does it go that high up or does it only go this high up, right? Either way, it just needs to be increasing. So I'm going to make it go up to here, right? Doesn't have to be perfect. Again, how do I know that it flattens out and it doesn't just shoot up like that when it approaches that? That's because I have a critical point right there, meaning it needs to flatten out, right? It needs to flatten out when it reaches to -2. So that's how that graph works, okay? Now, a common misconception about these problems is they'll say, knock me, how come these lines are above the x-axis when they're below the x-axis here and here, right? And you need to take into your mind right now, or take into account, the derivative does not tell you the function value. It only tells you when the function is increasing or decreasing. When is the function going up and when is the function going down? It doesn't tell you specifically if it's above or below the x-axis. So just because the derivative is negative doesn't mean the original function was negative. It just means the original function was decreasing, right? That's all we can tell. And the same thing that can be said when a function is increasing. We don't know that it's positive and increasing. We just know that it's increasing, right? It could be negative and increasing as well. We don't know. Okay, let's finish this off right here. From -2 to 4, it's just a big chunk of negative. So it's just a big chunk of going down, right? Going down, going down, going down until there, right? How do I know it's still there? Because I know it flattens out here. How do I know that it flattens out there but not flattened out here or flattens out here? I don't know. I kind of just sketch my curve as best as I can so that it reaches there. And if you did this on the test, any one of those 3 would be perfectly fine and perfectly valid for that sketch. Because all I'm really focusing on is the function decreasing on this interval. And as long as it's decreasing on that interval, that's perfectly fine. Okay, that's perfectly fine. So those are the sketches right there so far, right? And then the last part right here is to tell me the function is now increasing after that, so it's going up. Now, how steep is it going up? Is it that steep? Or is it this steep? Or is it this steep? Again, it doesn't have to be perfect. As long as it's increasing, it's good enough for me to see that I saw that there is a critical point here, critical point here, and a critical point here, and that it's increasing after that. And that would be my sketch for the function given the derivative. Given the derivative. How you guys doing? You guys okay with this? You guys not okay? You feeling all right? Somewhat. With this being completed, by the way, now you should be able to do most of the homework that I've assigned from 4.2 to 4.3, part 1 and part 2. There's only one problem that you might not be able to do, which is the thing I wanted to get to today, but we did not have enough time, which is the particle movement of something. I'm just going to throw that at you at the last minute for this lesson right here. But with this, though, you should be able to sketch graphs now. You should be able to take a look at a function and imagine what the derivative graph should look like, and vice versa. If you're given a derivative function graph, I should say, you should be able to imagine what should the original function look like. Okay, so we're going to kind of leave it there for you. Yeah, just going to kind of leave it there for you guys to see that and try to imagine it. We'll do some more practice problems on that. But before I let you go, I want you to get this last part right here. This whole idea of increasing, decreasing, right, can also be used for position functions, right? So this will be the last thing I'm going to leave with you guys right here. This is the applications, right, to particle motion. And this is the last thing I'm going to show you right here. So with particle motions, they give you a function as position. So it's usually like s of t or x of t or something like that to tell you what the position is of a particular particle, right? So for example, right, I could have something like this. S of t is equal to 2t cubed minus 14t squared plus 22t minus 5, right? And the idea is, if I'm looking at, for example, when t is equal to 0, right, the position is going to be equal to -5. So where is this thing located? It's located -5 from the origin. So if I have this particle, right, and here's 0, -1, 2, 3, 4, 5, right? When t is equal to 0, the particle is right here at -5, right? And then I can figure out, oh, when t is equal to 1, I plug that in to my function right there, and I see what I would get, and then it tells me if the function moved forward or if it moved backwards, right? So instead of doing that, because then you don't know if it moved forward at 1 or if it moves forward at t equaling to 0.5, you don't know if it went backwards then forwards, right? So instead of doing all that guesswork, we can use the first derivative test and the second derivative test to tell you where the critical points are, to see when does the velocity change. So if the velocity is positive, it's currently moving forward, and if the velocity is negative, the particle is currently moving to the left or backwards in the negative direction, right? So that's something that helps you out there. And then the acceleration will tell you if it's speeding up or slowing down if the signs match, right? So I'm going to kind of just throw this at you right now. Don't worry about too much of it. I'm just going to wrap it up here because I don't think we have enough time to actually do this problem. But let me get you this right here. Oops, that's not what I want, a screenshot. Let me go ahead and get you this right here real quick. That's not what I want either. Come on, buddy. Work for me here. There we go. So if you guys could. So in my old notes here, I didn't use s of t. I use x of t for my position. Same idea. It's just the location of it, right? So I'm going to go ahead and put that over here. So when a particle is moving to the right when the derivative is positive, and it's moving to the left when the derivative is negative, right? So think of this as your car, right? Like think of you in your car and you're going, we're going straight, by the way, we're not making any turns, right? So if the derivative of position is velocity, right, meaning how fast you're going, right? If your speed is 60 miles per hour, positive means you're going forward 60 miles per hour. If your derivative was a negative value, it doesn't mean, it just means that you're still traveling at that speed, but now you're traveling backwards, right? So if you had like a speed, a velocity of negative 60, that just means you're going 60 miles per hour in the other direction, right? That's all positive and negative is just a sense of direction. So when you take that into account, when we start breaking down first derivative values, right? First derivative values, this will give you the velocity. Okay, and if the velocity is positive, then your particle is moving to the right or going forward, we should say. And if your velocity is negative, then your particle is going backwards, right, or going to the left on my number line, I should say, right? And then if you can match the second derivative with the same sign, then that means that it is accelerating, right? You could be accelerating forward and you could also be accelerating backwards, right? And if they are different signs from each other, then you can say that the particle is decelerating. It's still traveling in whatever direction that it's going, but it's not traveling in that direction as fast, right? It's not traveling in that direction as fast. It's slowing down, right? So that's what we say. And that, of course, right here, when you do the second derivative, you're basically looking at the acceleration. I don't have no space there. But yeah, that's that for that one right there. And that should be the last thing that you should be able to take a look at and do the homework now. So please go ahead and take a look at that homework. If you're already done with the homework, good on you. Double check your answers, submit it. I should be grading those along the way. And I think I took the note from you guys, right? If you are not done with your homework by the end of this week, I will be putting it in as 0, but I still want to make sure that you guys understand that it's not your final grade. I accept all late work and I will give you full credit on it. But remember, you guys wanted to see the 0 so you guys can get a wake-up call if you guys can see what your grades are. And then you can actually see, doing it this way, once you submit it and I grade it, you can actually see your grade change. The only thing is, though, if you turn it in late, don't expect me to grade it instantly. I'll grade it when I get around to my grading schedule. So just keep that in mind. If you don't like seeing that 0, just turn it on time. If you don't mind seeing the 0 and knowing that you still get full credit, just make sure that you can still turn it in after I've already graded it, and you'll still get full credit. Okay, so that being said there, on Thursday, I kind of want to give you guys a quiz, and I'm kind of short on time, so there's a good chance that your quiz will have some questions from your homework, right? So hopefully you might want to take a look at that and see what it is that you need to know or what type of problems there are on there. And yeah, your quiz will be on Thursday. So come in on time. It will be the first 20 minutes. You will be submitting it, uploading your work, and it will lock out after 20 minutes. Okay, so make sure you show up on time on Thursday. Other than that, guys, that's going to be it for me today. Hopefully you guys are okay with this. If not, if this whole graphing the derivative and graphing the function thing is hard for you to understand, please stop by during the office hours today. I will be there, and we can go over it if you are having any extra questions about this. All right. Other than that, guys, I'm going to call it there, wrap it up there, and say have a good rest of your day, guys. I'll see you guys on Thursday, okay? I'll see you guys later. So long. Farewell. Bye-bye.